All right, welcome everybody to Intro to Space Navigation, Spring 2025, Lecture 19. I'm going to go ahead and share. And as a reminder, we're on out the different techniques that we need to be able to take a starfield image and then turn that into some estimate of which way our camera is pointed in inertial space. And we've had 3 different lectures already on this topic. One of them was really a lecture and a half on space cameras, and that is how to do the image processing to find the star pixels in an image, and then how to go from those pixels to directions in 3D space. Because really, we like to use bearing vectors as navigators or line of sight directions. And then, if we're going to navigate using stars, then there needs to be some sort of a star map. There has to be some compendium of star line of sight directions in some world frame. And we have those, and we talked about how to put together a star line of sight direction from information in, for example, the Hipparcos catalog. And then, in my opinion, the hardest part of the whole process is the data correlation step, which is, okay, you've got some stars in your image, you've got some stars in, the catalog, which one is which? And that one is definitely, I wouldn't say that it's more of an art than a science, but it's the most artsy of any of these, where there's several different approaches you could use. On the homework, you're kind of encouraged to do this, whatever way makes sense to you. And also, just to reiterate, on the homework, when you're trying to process an actual starfield image, I highly recommend that you work in groups. If you've been kind of lone wolfing the other homework assignments, don't do that here. I think it's going to be too much. So today we're just going to polish it off. And there's going to be, so we're going to go through kind of a lengthy derivation of how to solve what's called Wahba's problem. First of all, what is Wahba's problem, and then how do we solve it? But when the time comes to code this up in Python or MATLAB, it's like less than 10 lines. It's really pretty short to put together your attitude determination code. And that's it. And then after today, you will have everything that you need to survive and thrive on homework 4. So any questions before we get into today's topic? All right, neat. So lecture 19 is what's called Wahba's problem. So presumably, from the name of the lecture, there was somebody whose last name was Wahba who was having a problem. And we will talk about how to solve that. Actually, there's a fun kind of story. Well, not necessarily a whole story, but kind of a neat background on Wahba's problem. So this is the final Star Tracker lecture. So we've talked about we can process a starfield image to find EIC hat tilde. So this is the ith point in the camera frame. It's a unit vector, but it's a noisy unit vector. So this is what comes out of our image processing. That's lecture 16. And we can download a star catalog and make an invariant index. And we can find corresponding catalog line of sight directions. And that would be EII, so in the inertial frame, hat no noise. Okay? So the question is, what is our attitude? So you can think of it as this way. The measurement, generally as navigators, we're after some sort of equation that maps our state to our measurement, right? Our measurement is the true, oh, here I am writing U's again, sorry. Whenever I'm on autopilot, you'll see me writing U's. We're trying to do E's today. There we go. So EIC, the camera frame noisy line of sight vector, is the perfect measurement. And And there's going to be some sort of rotation. So some attitude transformation matrix from the inertial frame to the camera frame, and some just white noise. And this is what we're after. So given a whole bunch of line of sight directions in one frame and a whole bunch of line of sight directions in another frame, and we know they are the same line of sight directions, then there ought to be some 3x3 direction cosine matrix that maps from the first set to the second set, and we ought to be able to find the elements of that 3x3 matrix. So I like to think of it as, here we go, if you've got, well, let's just get into it here. I'm going to try to be quick. We will pose this as an optimization problem. Okay. So we know what what ought to be zero. What ought to be zero. So it seems to me that EIC hat tilde minus TI to C EII ought to be zero, right? All we did was move this over to the other side of the equal sign. So all we have left is our residual. We don't really know anything about that Gaussian white. I mean, we know that the, let me rephrase that. It is random. And so we're essentially saying the vectors minus the properly rotated catalog vectors on average should be zero. And so in order to solve this as a kind of minimizing the sum of the squares type of situation here, then we're going to create a cost function, which is J, which is some function of T I to C. And it is going to be 1/2 times the sum of every point in your image of all of this business, transpose R dagger, and then EIC tilde minus T I to C EII, like so. So something that ought to be zero transposed with itself. So if we have the right answer for T, then this cost function will be as close to zero as we can possibly get. That's the idea. So we're trying to minimize this business. So we would like to minimize this. So why don't we start with, remember that EIC minus T I to C EII, that's really just our epsilon. That's our noise, right? So you could rewrite this cost function as J is equal to 1/2 sum over every point in the image. And we've got just this residual transpose R, measurement covariance matrix. And it's not transpose, it's actually a pseudo inverse. That's the pseudo inverse from the end of lecture 18. Which I recognize is still in. I'd like to go through and change these from U's to E's to keep everything consistent. But we talked about RI dagger. That's the pseudo inverse of our measurement covariance matrix. That's what we're about to plug in here. So that's going to come back to help us. And then this should be EI. Okay. Now let's go through, and that measurement covariance matrix is really 1/2 sum over all I, EI transpose, and then this is going to be sigma I squared. If I'm not mistaken, it's identity matrix minus E transpose, and I think it is the measured. Yes, it is the measured. Okay, where, oh, but it's 1 over sigma I squared, I see. Okay, so 1 over sigma I squared. And then we've got EIC transpose, and then all of this times epsilon I. Okay, so that's what we're trying to minimize. Okay. Now we can go through and pull out the 1 over sigma I squared, and we can say, okay, let's rewrite this a little bit. J So 1/2 sum over all I, 1 over sigma I squared. And then we can say, well, this is really epsilon transpose epsilon minus epsilon transpose EIC, EIC transpose epsilon. Just like that. But here's the thing. Remember that epsilon transpose EIC is equal to 0. So what does this mean? Because this might we might be far enough into the math that this is starting to seem a little arcane here. So remember from our discussion measurement model, which again is kind of half E's and half U's now, so it's a little bit of a mess. Sorry. This all in one letter. My old notes had U's and my new notes have E's. That's the problem. So what we're saying is that the noise on our true line of sight direction, because we're moving from a unit vector to another unit vector, must be perpendicular. So at least to first order, this epsilon I is perpendicular to UIC, or you could say epsilon I transpose EIC is 0. Okay, so that saves us right here because this part is now all 0. So this is about to get a little bit friendlier to work with. So our cost function, which we're trying to minimize, is now 1/2 sum over all points, 1 over sigma I squared, where again, that's our bearing error. That's how much we don't trust these measurements. And then epsilon I transpose epsilon I. Okay. But now we can unpack this epsilon I business. I'm going to resubstitute the full thing back in because we're building towards an equation which we're about to box and give it a name. So J is 1/2 sigma over all I, 1 over sigma I squared, and then we've got EIC minus T I to C EII, that's an E, and then transpose EIC minus T I to C EII. Okay. Or if we felt like trying to clean this up a little, that our problem, and this is the one we're going to box, is the minimum of our cost function, which is a function of T I to C, is equal to 1/2 the sum over all I, 1 over sigma I squared, and then it's going to be just the norm of this vector, EIC minus T I to C EII. There it is. And this gets boxed. Okay. So how do we solve a minimization problem of this type? So all we did was we took the original problem, which is set up as a maximum likelihood estimation problem. So not only are we taking into account our residuals, we're trying to minimize the sum of our squared residuals, but we're also taking our measurement covariance matrix into account. So we take this equation, and we're trying to minimize this. And all we did was taking the Quest measurement model, then we end up with this equation, which is a little bit friendlier to work with. So we're saying, okay, take the norm of the residual. So after you've reprojected your catalog line of sight directions into your camera frame, then what is the residual error left over? And it's each of those normalized divided by our bearing error squared, sum of those, and then 1/2. That's the entire equation. And this was first introduced, or I should say, this problem was first formally posed in 1965 by a graduate student, which immediately, when I heard this, I thought, my goodness, I was not this far deep into the math as a graduate student that I was posing new questions about attitude determination. But this equation was posed by a graduate student named Wahba. And that's Wahba's problem. Right? And what we're after is a solution to Wahba's problem. We're actually going to go through two different methods of solving this, just like how in the GPS lecture for trilateration, we showed nonlinear least squares and Bancroft, and you can use whichever one you like. I'm going to show two different methods that you could use on homework 4, where once you have your vectors, you can use either one you like. One of these is my favorite, but it's really up to you, whichever one you want to use. But questions up to this point, or are we feeling okay? Okay, so this next part's going to be a bit of a mathematical roller coaster. It's going to be one of the more dense lectures, but you'll see that when we're done, the solution's actually really nice and elegant. So our first solution strategy is solving for the attitude transformation matrix. Using singular value decomposition. Okay. So we begin by restating Wahba's problem in vector form. Okay. So I'm going to say, let there be some matrix A, which is EIC, or sorry, not I, but 1, and then E2C, all the way to ENC. So this is just taking all of your line of sight directions, which is your star line of sight directions in your camera frame, and then just concatenating them side by side to get a wide but short matrix. So this is going to be a 3 by n matrix, where n is the number of stars you've been able to identify. And then the matrix E is going to be E1I, E2I, all the way to ENI, like so. Also 3 by n. So this is just your line of sight directions in your camera frame and those same line of sight directions in the inertial frame. We will also define a weighting matrix. And that is W, which is going to be an n by n diagonal matrix, is going to be 1 over sigma 1 squared all the way to 1 over sigma n squared. You know? And so the new Wahba's problem is going to look like this. The minimum J, and I'm just going to say of T, we know which T we're talking about, is 1/2, and then it is the weighted A matrix minus attitude transformation matrix times the weighted E matrix. And then this is the Frobenius norm, because what we're going to end up with here is a matrix. You can't just say take the norm of a matrix. You have to specify what type here. So I'm going to say this. Frobenius norm. Okay. So we're going to keep pushing. This is going to make more sense in a second here. So first, we can define A prime is AW and E prime is EW. just to simplify things a little bit, we know that we're applying these weights to our line of sight directions. And so you're never going to see A by itself. It's always going to be AW. So let's just save some ink and write it this way. So now our problem looks like minimum JFT 1/2 A prime minus T E prime squared, and that's Frobenius norm. Okay, all right. Now, remember, so basically we're trying to find T such that all of this is as small as possible. Nowhere in here are we enforcing that T is a 3x3 direction cosine matrix, right? We're just saying T is a matrix. Find the numbers that make this true. So we'd like to enforce this constraint. So remember that T must be orthonormal So the way we could enforce that is to say that T transpose T should be the identity matrix. Okay, so in optimization, whenever we're trying to make some number as small as possible while obeying a constraint, maybe you've seen this if you've taken design optimization, or you can just take my word for it for now. Essentially what we do is we add a term to our cost function, which becomes large if we violate this constraint. That's essentially it. So not only are we trying to minimize this, but also if we violate the T constraint, then you get a larger cost function too. Otherwise, you're not punishing the cost function from just making T anything, right? So we enforce this with what's called a Lagrange multiplier. And all this is, like I said, is just enforcing the constraint with a new term on the cost function. So now I'm saying min J of T is 1/2 A prime minus T E prime Frobenius norm squared plus the trace of some new term lambda, capital lambda, and then T transpose T minus I, okay, where this is our Lagrange multiplier. Okay. Now we can also shorten things because we're about to, maybe you can already see where we're going with this. Whenever we are doing an optimization problem or a minimization problem of this type, we're probably going to take a derivative and set it equal to 0. I have no idea how to take the derivative of a Frobenius norm. I'd rather not do that. So let's take a minute to substitute. The Frobenius norm can be rewritten as just a vector Frobenius norm squared is the trace of x transpose. Okay, so our problem now becomes the minimum J of T of 1/2 times the trace of, okay, so what's about to happen here? It's A prime minus T E prime, and then A prime minus T E prime transpose. And then we can't forget our Lagrange term, trace lambda T transpose T minus I. Okay, still ugly. And we're about to have to take a derivative of this. So it would be helpful to review a few useful properties of a trace. So there's a great resource. I can't remember if I mentioned this before, but I'll mention it now, called the Matrix Cookbook, which you can go look up online. I think it's University of Waterloo. That sounds right, but I could be mistaken. But if you Google Matrix Cookbook, it should be the first hint. And it's basically a textbook that these folks have put together on just a million different rules when it comes to matrix operations. And we're going to steal a few of them right now. So let's pause and review 3 useful properties from the matrix cookbook. And then after this, we're taking the derivative, and really you're taking the derivative. So I hope people are locked in. Let's see. I'll get us started, but then after that, it's going to be on you. Okay, if we're taking the derivative with respect to x of the trace of a x transpose, that's just a. Okay, these are just from the cookbook, given them to you without derivation. Hope this makes sense. The derivative with respect to x of the trace of x a x transpose is going to be x transpose a transpose plus a. Okay, and then the derivative with respect to x of the trace of a x x transpose is a plus a transpose x, where, just want to be clear, a and x are both matrices. Okay, these are going to be helpful. So in light of this, we will expand our cost function before taking a derivative. So these while they might look confusing, these are here to help us. Okay, so we've got the trace of a minus TE transpose. Yeah, that needs to be expanded. So let's go through and get this into individual terms. I think I might be able to fit this on a single line if my monitor's wide enough here. So it's the min J of T is equal to 1/2 open curly bracket. And what's the first bit? It's going to be the trace of A prime transpose, right? We're basically doing a FOIL operation, right? First, outer, inner, last. That's our first term. Then we've got the trace of A prime and then E prime transpose T transpose. Because remember that when you have, A, B transpose, that's B transpose A transpose. Just want to be clear about that. So that's this term. And then we've got minus the trace of T E prime A prime transpose. So these are kind of our outer and inner terms. And then we've got our last term plus the trace of T E prime transpose T transpose. And that ends our curly bracket. But then there's also plus the trace of lambda T transpose T minus the trace of lambda. Okay, that is our cost function. Fun. All right. So to find the optimal value of T, we apply the first differential condition. Which would be the derivative with respect to the thing we're trying to optimize of our cost function is 0. Okay. So dj dt is equal to 1/2 open curly brackets. All right, there's 1, 2, 3, 4, 5, 6 terms here. I will do at most 2 of them. I'll do 1 to warm us up, and then if we're feeling shy, we can do 1 more. Oh, actually, I think I should throw you right into it because the first term is really easy. Let's get a different person for each term. What is the trace? So the trace of A prime transpose, derivative of that with respect to T. This one's very simple.
That's just 0.
It's just 0, right? Yeah, exactly. There's no T in that term. So first term is 0. Good. And then let's see, what's going to happen next? So this next term, we've got A, E transpose, T transpose. So let's think, which one of these does that look like? Kind of looks like the first one to me. So anyone want to guess what this next term is?
A prime?
It's going to be A prime and then also E prime transpose. Because you could think of it as we're keeping this bit and then just dropping this. That make sense? Let's see. And then similarly, for this next bit, we have T, E prime, A prime transpose, but that is just the transpose of what we just saw, right? If you take AET transpose and you transpose that, you get TEA transpose, which the trace of a matrix is the same as the trace of a matrix transpose. So actually, this is that too. So 3 terms down. This next one's ugly. We've got the trace of TE transpose T transpose. Which one does that look like? This one's tricky.
I'm trying not to answer again, but it looks like the third one.
Looks like the third one. Let's see. To me, it looks a little bit more like the second one to me, unless I'm looking at it the wrong way. Because you've got the thing in question sandwiching some other stuff that we don't care about. So you've got T, stuff
You're
that we
right.
don't care about, T transpose. So I would conjecture that this is T transpose, and then we've got E prime transpose. Oh, but then that should be transposed. So it would look like this. Like that. Okay. And then that ends our curly bracket. And then we got hopefully something a little bit easier. Okay. The trace of something we don't care about times T transpose T. Well, let's see. Well, how would that work? That's not quite the same thing as the third one, but it looks pretty similar because the third one here is something we don't care about, and then X transpose. So if we just said that this was the derivative with respect to T transpose, this would give us what? It would be lambda. Oh, well, we can drop this last term too. The last one's also 0. I think this one is going to be lambda plus lambda transpose T. That equals 0. Which, this is still a bit of a mess. We need to kind of recover from this. So actually, this part here is negative 2 A prime E prime transpose, and then this cancels with this. And then this bit here is going to be 2 T E prime transpose. Yeah. And then this 2 also cancels. Now, should that be 2 or should that be T or T transpose? I think it might be T transpose. Nope, I have it as T. Okay, cool. We're going to keep moving with that for now. And then we've got lambda plus lambda transpose T. This bit doesn't really simplify. So recover from this mathematical mess here. So we can simplify this a bit. by defining 3 new matrices. Okay. P, which is defined as E prime transpose. Q, which is defined as lambda plus lambda transpose. And then B, which is defined as A prime E prime transpose. And this B is actually going to be the star of the show moving forward. This gets a name. This is called the attitude profile matrix. We're going to be seeing a lot more of B moving forward. Stand by. Okay, so let's try to simplify this a little bit. Now, our equation is okay. We've got negative A prime E prime transpose. Well, that's just the attitude profile matrix. So this first term is negative B. The middle term is going to be T E prime transpose, but we said E prime transpose is P. So I'm going to call this T P. And then the last term is lambda plus lambda transpose, which we're going to call Q T equals 0. Or you could say B is equal to TP plus QT. Okay. Or if you wanted to, you could say that B T transpose is equal to TP T transpose plus QT T transpose. But TT transpose is going to be the identity matrix. Now here's something neat. Q, which is a matrix plus a matrix transpose, this is going to be symmetric. But also, TPT transpose is also going to be symmetric. So therefore, we know that BT transpose is symmetric. Okay. If that's the case, we should be able to do this. BT transpose times TB transpose is equal to TB transpose times B T transpose. Or if we simplify this, because T transpose T is the identity matrix, then we get that B transpose is T B transpose B T transpose. Okay. Again, starting to feel like we're going way out into the weeds here, but we're actually pretty close to bringing this in for a landing. So keep bearing with me here. We can perform eigendecomposition on B transpose and B transpose B. Okay, so what would that look like? We'll say that B transpose is U D U transpose. So eigenvector matrix, eigenvalue matrix, eigenvector matrix transpose. B transpose is eigenvector matrix, eigenvalue matrix, eigenvector matrix transpose, where D is eigenvalues, which is the same for both. Okay. So we can replace this and we can say U D U transpose is equal to T V D V transpose T transpose. Where, okay, so we have D in common between both of these equations. So this bit must equal this bit. So therefore, U is equal to TV. And you can think of it this way. T is equal to U V transpose. Okay. Now, there are some more steps, but actually we're done. This is it. You might have noticed it just kind of happened throughout all this math. All of a sudden, here we have an equation. The attitude transformation matrix, which we are after, is UV transpose, where U comes from the eigendecomp of BB transpose. V comes from the eigendecomp of B. Oh, whoops. Sorry. No one called me out on my typo. This is transpose goes there. Sorry about that. Okay. So V comes from the eigendecomp of B transpose B. U comes from the eigendecomp of BB transpose, but it's even easier than that. So where U and V wow, I can, sometimes I'm looking at my notes while I'm writing and it shows, sorry. Come from eigendecomp of BB transpose and B transpose B, or directly from singular value decomp of B. So if you value decomposition, you say the attitude profile matrix is U singular value matrix V transpose, then what we do is just get the U, get the V, drop the S, replace S with identity. Actually, we're going to replace S with a variation on identity. You're going to see in a second. We are going to ensure that T is right-handed by introducing the matrix M. Where M is the identity matrix, except this term is determinant of U multiplied by determinant of V. And then 0, 0, 0, 0, 0, 0. Okay. What this does is if we say U V transpose is T, which you might notice, U V transpose is basically B except for our singular value. So we're really just scaling it down. Our attitude profile matrix is already most of the way to the answer. We get our attitude profile matrix, we get U, S, and V transpose from singular value decomposition. We drop the S, then we force it to be right-handed by replacing S with M. And reintroduce our subscript and superscript, is the inertial to camera matrix comes from U, M, V transpose. And that is our SVD solution, which admittedly was a bit of a pain in the butt getting here. But if you look at our final answer, it's like B is just this. And I'm actually going to highlight this one here too. B just comes from all. Oh, there's a lot here. You take your camera frame unit vectors, you squish them side by side. You get your inertial frame unit vectors, you squish them side by side. You weight them by how much you don't trust your individual measurements. E prime, okay? A prime, E prime transpose is attitude profile. Singular value decomp, reconstruct, boom, you're done. Like 5, 6 lines in MATLAB or Python. That's about it. So it really is that simple. And I think this is a great pausing point because right now you have the minimum success criterion for homework 4. The rest of this lecture is comments on this solution and then an alternative solution which you might like better. But let's pause here for questions. We okay? Cool. All right. I have one more page of notes and then it's time for a break. I want to talk about, so whenever we solve a estimation theory problem, we get a solution, but we also like to come up with a metric for our uncertainty, right? Our covariance. So how much do we not trust our singular value decomp answer? And I can't tell you, but F. Landis Markley, who wrote a paper about this in the 80s or 90s, he can tell you about this. Your way, which came from his work, which describes the uncertainty in this solution. So you've got some uncertainty in your camera frame unit vectors, and then you've got some viewing geometry problems, right? Because you're only seeing so much of the sky from your camera. And somehow that's going to tell us how much we don't trust this T answer. So remember, so we'll have a brief discussion on uncertainty in the SVD solution. And these equations are presented without derivation, so we're just going to bear with me for now. So the first is, we said that our attitude profile matrix is U S V transpose, where I'm going to say that S, the singular values, is just this matrix, S1, S2, S3. Okay. Then I'm going to say let D be defined as determinant of U, determinant of V, which is this third term on M. And let S prime be S1, S2, DS3, 0, 0, 0, 0, 0, 0. Okay. So all we're doing here is we're creating this, like, if M is the identity matrix forced to be right-handed, now S prime is the singular value matrix forced to be right-handed. Okay. Also, we will define D as S2 plus D S3, S1 plus D S3, and S1 plus S2. 0 is on the off diagonal. Okay. So we've made some new friends, and that would be our S prime matrix and our D matrix. Okay. Now we can combine catalog error, catalog uncertainty, and camera or sensor uncertainty by this sigma total, how much we don't trust our measurements, which is going to be 1 over the sum of, let's see here. Oh, do I have? Okay, I see. Yep. I equals 1 to n. So this is all of your star measurements of sigma I squared plus sigma c I squared, and then -1. Where basically for each line of sight measurement, here's how much we don't trust that line of sight in the camera frame. Here's how much we don't trust it in the inertial frame. However, I will add that in practice, catalog bearing error is negligible. Compared to camera bearing error. So we can simplify. and we get that sigma total squared is now just a function of the individual uncertainties of our star. So it's going to look like this: 1 over sigma C1 squared plus all the way up to 1 over sigma Cn squared. So those are all of our camera line of sight direction uncertainties added together like so. So we can build this sigma total. Finally, our answer is P, our covariance, is sigma total squared D inverse identity matrix minus S prime D inverse again. Now this gives, first of all, you might be thinking, this is a 3 by 3. Now we know that when our when what we're after is our position, which is 3 by 1, then our covariance is a 3 by 3. It's going to be like X uncertainty, Y uncertainty, Z uncertainty, XY covariance, XZ covariance, YZ covariance, right? We get a 3 by 3 covariance from a 3 by 1 state. So if we have a 3 by 3 state, then how do we get a 3 by 3 covariance? And the answer is that we don't. It's not this case. This is not the covariance of the attitude transformation matrix. This is the covariance of the angle vector, because we need to start with a 3 by 1 to get a 3 by 3 covariance. So this gives the covariance of the angle vector associated with our direction cosine matrix T. So this is not the uncertainty in T, this is the uncertainty in the angle vector representation of T, right? Because we've talked about how a direction cosine matrix has 3 degrees of freedom. You could express it as a direction cosine matrix, which is 9 numbers, 6 constraints. You could also express it as a unit quaternion, which is 4 numbers and 1 constraint. Or you could express it as roll, pitch, and yaw angles, but then that also carries the ambiguity about what's your rotation sequence. Or you could use angle vectors, which is a axis, which is a 3 by 1 with a unity norm constraint multiplied by an angle. That gives you your angle vector. That's where we are. This is all the way back in lecture, lecture 4. So you might say, okay, great, Paul, that all sounds good. Why do I care? Well, there's one extra step that we can do. This can be collapsed into a scalar by theta error is the square root of the trace of this uncertainty matrix, where theta error is an angle, is the angular uncertainty associated with our Wahba solution. That's it. So this is not required of you on the homework, totally optional. On the homework, you're done. Just calculate T and then you're done. But if you're curious, you can go the extra mile T in that T. That's it. That brings us pretty close to the top of the hour, and we've been doing some hard math for a while. I think we should take a break, and then I've got 2 more pages on a quaternion heavy method of solving this problem. But why don't we take a break for about 5 minutes? Let's say back at, so it's about to be 7 for you, right? So it'll be maybe 7:04. Give me an extra minute. Sorry, 1 second. I'm just getting organized and it's taking longer than I thought. Just be an extra moment getting ready here. Okay, all set. So, welcome back, everybody. It is time to talk about another way of solving Wahba's problem that was invented in the 1970s by a guy named Paul. And obviously, I'm a fan of that. Us Pauls need to stick together. So we can also solve for the quaternion. Which is referred to as the Davenport method. Okay, so this solution to Wahba's problem was developed in the early 1970s by Paul Davenport. Right. So as a reminder, the problem looks like the minimum of J of t is 1 over sum of all your stars, I, 1 over sigma I squared. And we have the norm of EIC minus T from I to C, and then EII squared. And that is not a matrix, so we don't need the Frobenius norm. And we're about to have a lot of attitude transformation matrices, so we're just going to abbreviate as T. Okay, and we can expand. Min J of t is 1/2 sum over all I, 1 over sigma I squared. And then this is about to be a FOIL situation. So this is going to be EIC transpose EIC minus EIC transpose T EII minus EII transpose T transpose EIC, and then plus EII transpose T transpose T EII again. Okay, and we can simplify. This is getting kind of ugly. So any unit vector dotted with itself is just going to be identity. You know what? That's supposed to be the number 1, but I can do better. There we go. Any unit vector dotted with itself is identity. Also, remember that T transpose is the identity matrix. Sorry, EIC transpose EIC is 1, because this is a scalar equation. T transpose T is the identity matrix, so you can kind of ignore it. And then you've got, again, a case of a unit vector multiplied by itself, or dotted with itself, which is just 1. Okay? And similarly, this is actually the same thing twice, right? This is kind of the 2bx, you know, whenever you do your foiling, that sort of thing. So this can be combined. So we get the minimum J of t is 1/2 sum over all I, 1 over sigma I squared. And then we get 2 minus 2 EIC transpose T EII, where 2 cancels with the 1/2, so this is just going to be a 1. This is going to be a 1. Well, you can kind of ignore the leading 1, right? Does that help us? So we can actually split this up. We can say that this is a minimum J of t is equal to the sum over all I 1 over sigma I squared minus sum over all I 1 over sigma I squared EIC transpose T EII. So all we're doing is we're taking the 1 minus some stuff and then breaking it up into two terms, the 1 and then the stuff. Now what you'll notice is this first bit does not have t in it. So what that means is if we were to try to minimize it, this whole first term is just going to be stubborn as a mule. It's not moving. This is constant with respect to t. And we're going to name it lambda naught. Okay, we don't really care about it. And you're going to see when we take derivatives later, it's going to go away. Or wait, let's see. Oh, you know what? I don't know that we are taking derivatives later. Oh, no, we definitely are. Okay, I was going to say, I couldn't find the derivatives in my notes. Like, I'm pretty sure we're at some point going to be taking a derivative. Rest assured, we are. Don't worry. Okay, so that simplifies things for us a little bit. Now, both terms are scalars, right? Lambda naught, great. We know it's a scalar. It's the sum of all of the 1 over sigma I squared. It's great. This other bit is going to be vector transpose matrix vector times a scalar. So that's a scalar, and then it's the sum of a bunch of scalars. So all of this is a scalar. So because all terms are scalars, we can take the trace for free. So the trace of a scalar is just a scalar, but you're going to see we're going to play some fun tricks with the scalar properties or with the trace properties in a minute. So this problem became the minimum J of t is the trace of lambda naught minus the trace of sum over all I, 1 over sigma I, and we've got E IC hat transpose T E I I. Okay? Or we can try to clean this up. This is really the trace of lambda naught is just lambda naught. It's this last term that I'd like to work on. It's going to be the trace of, and we're allowed to do this because of cyclic permutation, right? So the trace of A times B times C is the trace of B, C, A, right? If you just cycle A through to the end, and so on and so forth. So cyclic permutation. So we're actually going to cycle T out front. So this becomes the trace of T times the sum over all I, 1 over sigma I. This should be squared. And then we get EIC transpose, or sorry, getting ahead of myself here. This should be EII. No, there it is. Okay. Okay, so we just cycled things around. So you can imagine E goes to the end, and then T comes out front. That's the idea here. And this simplifies a little bit, where all of this, the sum over all sigma I of the inertial frame vector and then the camera frame vector transpose, this is going to be a matrix, which we're going to call B transpose. And you might be saying, okay, let's be careful. You used B in the last derivation. Don't use B again unless this is the attitude profile matrix. Well, guess what it is? So guess who's back? B is back. Tell a friend. This is the attitude profile matrix. Okay, so the problem just became the minimum J of T is lambda naught minus the trace of T B transpose. Okay, now it becomes quaternion o'clock. So recall that, let's scroll down here, recall that an attitude transformation matrix can be reconstructed from a quaternion using this equation from lecture, I think it's 4. Yep, using this equation from lecture 4. Quaternion scalar squared minus quaternion vector transpose quaternion vector. You know what? I'm going to be really lazy and just do this. Like this. There it is. Pop. There's me being lazy. So T can be reconstructed from the vector and scalar parts of a quaternion according to this equation. Okay. So this is where we're going to skip a few steps. And I know you hate it when I skip steps, but just, I mean, we got to get you out of here at some point. We can substitute this equation into our cost function. And after several steps, this looks like this. The minimum of J of Q, where Q is the whole quaternion, not the scalar or the vector part, right, is equal to lambda naught minus Q transpose K Q. Okay. Where K is called the Davenport matrix. And is formed according to, okay, K is equal to S minus mu times the identity matrix 3 by 3. And then, let's see, do we want to do it? Hang on. Sorry, stand by, pause. Maybe don't write that down. Get ready to erase. Okay, you know what? No, sorry. Not a mistake, but this is a scalar last equation. I would rather do it scalar first. It's my preference. This is going to be mu. This is going to be Z transpose. This is going to be Z. And then this is going to be S minus mu I 3 by 3. Where mu is a scalar. So scalar 3 by 1, or sorry, 1 by 3, 3 by 1, and then 3 by 3. Creates a 4 by 4 matrix. So this assumes scalar first. Where S is attitude profile matrix plus itself transposed. Mu is just the trace of the attitude profile matrix. And then Z is an interesting one. Z cross is B transpose minus B. So you'll have to do an extra step. You say B transpose minus B is equal to Z cross. Let me just extract Z from Z cross and then pop it in here. But hopefully you see this is not that many lines, right? So in the attitude profile matrix, you take the singular value decomposition, you recreate this M matrix, which is almost the identity matrix, except there could be a -1 here. And then you put those back together to get T. In this, we build the attitude profile matrix. After 3 more lines of code, we can build the K matrix. And now, how does that help us? We still haven't quite solved the problem yet, but we're very close. So we still have to do our derivatives. Don't worry, I did not forget about the derivatives. So we're not done. But we have a well-posed optimization problem. Also, before proceeding, we must enforce the unity norm constraint. Right, so remember with T, we had to enforce that it was a proper orthogonal matrix. In this case, we need to enforce that it is the quaternion is a scalar quaternion. So our cost function is going to look like the minimum J of Q is equal to lambda naught minus Q transpose KQ plus lambda times Q transpose Q minus 1. So this whole term should be 0. If it's not, then this third term is going to bite us in the butt as we're trying to minimize. That's the idea. So that kind of incentivizes your equation to obey this constraint. Okay. We apply the first differential condition. Okay. Which is delta J delta Q is equal to what? Okay, first term, derivative of a lambda naught with respect to Q. Y'all can shout it out if you know it.
0?
It's just 0. Yep, lambda naught has no Q in it. Good. Next, derivative of basically X transpose AX. So that kind of looks like AX squared, which we know becomes 2AX. So any guess as to what this bit's going to be?
2KQ vector?
It's going to be 2. In this case, we basically drop the trailing Q. So instead of KQ, it's going to be Q transpose K. Very good. Q transpose K transpose. Got to clean that up. Okay. And then we can do, okay, derivative of this last one. So it's going to be Q transpose Q with respect to Q. What is this? What derivative do we get here?
Q transpose?
Yep, it's going to be Q transpose, but then we've got the 2, right? So this would be 2 lambda Q transpose. And then 0, right? Because lambda is going to be 0. There we go. There's our whole thing. And then this equals 0. So if we want to clean that up, that's the same thing as saying that Q transpose K transpose is equal to lambda Q transpose. Or KQ is equal to lambda Q, which should look a little familiar. This is an eigenvalue eigenvector problem. Okay. So we know that our solution, Q star, must be one of 4 eigenvectors of the attitude profile matrix, or sorry, the Davenport matrix. But which one? Okay. So let's think about it. If we knew the solution, then let's go through and try to basically plug this back into our minimization problem. So let's just try to minimize this for now. Minimum J of Q is equal to, remember, it's lambda naught minus Q transpose KQ. Okay. But we know that KQ is equal to lambda Q, right? Where lambda is going to be our eigenvalue, and there's 4 of them. So it could be lambda 1, 2, 3, or 4. So let's replace this with lambda naught minus Q transpose lambda Q. Or we could write this as lambda minus lambda Q transpose Q. Oops, clean that up. But remember that this is just 1. So our problem becomes minimum J of Q is equal to lambda naught minus lambda, where we have no control over lambda naught, right? That is our term that's just kind of been following us through the whole minimization. But lambda is the eigenvalue that we've selected. So if we want to make this as small as possible, then this should be, because there's a minus sign in front of it, should be as large as possible. Okay, so finally, as J, we want the largest eigenvalue of the Davenport matrix K. So thus, Q quaternion from the inertial to the camera frame is the eigenvector associated with the largest eigenvalue of the Davenport matrix. Okay. And that's it. So to review this algorithm, even though there's a lot of derivation, we build the attitude profile matrix the same as we do with the SVD solution. From there, that's 3 or 4 more lines of code to build K. You do eigendecomp on K rather than doing SVD on B. And then you just keep the eigenvector corresponding to the largest eigenvalue, and then you're done. That's it. Now on homework 4, what I ask for is the quaternion from the inertial frame, the ICRF frame, to the camera frame at the time the image was taken. And it's your choice. Now, my personal preference is to do the singular value. It's fewer lines of code. You get T, and then you just pop that into your DCM2 quaternion script that you probably know, and then just do that. But this method will natively solve for that quaternion. It's totally up to you. And these are just 2 methods. There's more out there. These are just 2 that I thought would be fun to share. But my main point is that solving Wahba's problem is generally 10 or fewer lines of code. Doing your image processing is a bigger bear. Building your catalog, also a bit of a pain. Your index search is the hardest part by far on homework 4. Anyway, that is pretty much it for this lecture. Anybody have any questions pertaining to this lecture? Otherwise, I'll stop. We could talk about homework 3, have a little office hours. All right, somebody who is in a hurry to leave, you're free to go. But if you want to stick around and talk about homework 3, that is fine.